Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. I am Dr. Muhammad Ali Hashmi from University of Education Lahore campus and will be teaching you this lecture online. I hope you all will be fine. You all know the current situation of the global pandemic due to which we are at this stage of taking online classes. This is the time we need to ask Allah to forgive us all and save us all from this pandemic. Also, take all the precautionary measures set by the government to stay safe. Do not go outside unnecessarily. Wash your hands frequently. Social distancing is the only solution to this pandemic at the moment. May Allah subhanahu wa ta'ala keep us all safe from this. Ameen. We are studying mechanisms of organic reactions, and in this particular subject, today's lecture is about oxidation and reduction. This lecture includes the following main types of reactions. So today's lecture will be on oxidation and reduction topic, but in the oxidation and reduction, we are going to specifically see the reduction reactions that involve replacing oxygen by a hydrogen, and oxidation reactions in which a hydrogen is replaced with the oxygen atom. So these kind of reactions will be our main focus in the current lecture. So if you look at the oxidation reduction reactions, we may define them differently in organic chemistry and in inorganic chemistry. So if you look at inorganic chemistry, redox reactions or oxidation reduction reactions, they are comprised of two parts. One is a reduced half and the other one is the oxidized half. So they always occur together, like oxidation and reduction is happening at the same time. Reduced half gains electrons and the oxidation number decreases, while the oxidized half loses electrons and its oxidation number increases. So that is the main point in inorganic chemistry. If there are certain ways to remember these oxidation reduction reactions in inorganic chemistry, like we can use the mnemonic devices. Oil rig. Oil rig means the oil is oxidation is loss. Rig means reduction is gain. So that is very easy, that in oxidation you lose electrons. In reduction, the electrons are gained. Similarly, there are other devices like Leo says jar. Leo means loss of electrons is oxidation, while jar means gain of electrons is reduction. That means reduced. So at the end, there is no net charge in the number of electrons in a redox reaction. Those given off in the oxidation half reaction are taken up by the another species in the reduction half reaction. So overall net charge remains the same. If we move to the organic chemistry, there the oxidation and reduction have different and more convenient definitions for organic chemists. So in organic chemistry, we can define the oxidation as either addition of oxygen, loss of hydrogen, or addition of halogens. So all these processes will be termed as an oxidation reaction. Similarly, reduction is the exactly opposite. That may be defined as number one, addition of hydrogen, loss of oxygen, or loss of halogens. These all reactions will be termed as the reduction reactions. Next, we move on to reduction first. In this lecture, we are going to discuss the reduction of organic compound. So there are various reducing agents which are used in organic chemistry. Some very common ones are given here. The first one is sodium borohydride, NaBH4. It is very famous reducing agent which is used in organic reductions. The other and very powerful reducing agent is lithium aluminium hydride, LiAlH4. So that is also used in organic chemistry, mostly in the carbonyl compounds. And you all know, as you have studied in the undergrad classes, that hydrogen gas can be used with a palladium catalyst to reduce the double bonds. So these different reducing agents are used according to their mechanisms of actions and as per need in different organic reactions. So the reactions in which the oxygen is replaced by the hydrogen, those include the reduction of alcohols to alkanes. If we oxidize alcohols, we reduce alcohols to alkanes, alcohols are generally more oxidized than alkanes, but less oxidized than the corresponding carbonyl compounds. At the end, we can get carbonyl compounds by oxidizing alcohols. So we are going to compare the alcohols and their counterparts, which one is more oxidized and which one is more reduced. So if you see the oxidation states of these organic molecules, you will know which one is more oxidized and which one is more reduced. So we are going to see that on the next slide. Here, if you look at this slide, so this is an alkane, and which is oxidized to an alcohol, which is in turn oxidized to an aldehyde, and then it is oxidized to carboxylic acid. So if we go this way from left to right, that is oxidation happening. But if we move from right to left, that is the reduction happening. So we can see these reactions in both directions. Firstly, look at the alkane. It has no bonds to oxygen atoms. I mean, that carbon atom which we are considering, it has no bonds to the oxygen atom. And if we look at the primary alcohol it is producing after getting oxidized, it has one bond to an oxygen atom. So it is more oxidized than alkane. If we oxidize this alcohol, we get a carbonyl compound, that is an aldehyde here. So in this aldehyde, the carbon atom has two bonds to the oxygen, while the alcohol had one bond to the oxygen atom. So we can say that the aldehyde is more oxidized than the alcohol. And if we move forward, the carboxylic acid is having three bonds to the oxygen. This carbon is having three bonds to the oxygen. So carboxylic acid is the most oxidized of all these compounds. Similarly, these reactions can happen in alkanes, secondary alkanes, which produce secondary alcohol, and on oxidizing that secondary alcohol, you end up with a ketone. And if you use a tertiary alkane, you can end up at the tertiary alcohol, but after that you can't really oxidize this easily. Now we move on to the reduction of alcohols. Reduction of alcohols, first remember this, that reduction of alcohols is not easy, it is rare. Why? Because it removes the functional group. I mean, the whole functional group is gone from the alcohol and it is changed into something else. So it is not very common reaction, but it can be accomplished if necessary using one of these two common methods. So we'll look at these methods where you can reduce an alcohol. First one is, if you look at the reaction given at the bottom of this slide, you will see that we have an alcohol, cyclopentanol. So we can reduce it into two steps. The first step would be its dehydration. If you dehydrate this alcohol using sulfuric acid, and this you will end up with an alkene. So this reaction is a, a very common reaction you would have studied in the fundamentals of organic chemistry, that if you use sulfuric acid here, this OH can be protonated and it will leave from here and with a hydrogen from a vicinal carbon atom. So a water molecule will leave and you will get an alkene. And from this alkene, it is very easy to get an alkane by hydrogenating it in the presence of a metal catalyst like platinum. So this is the first method where you have replaced an oxygen atom by a hydrogen atom. So if you look at the original molecule, cyclopentanol, there was an oxygen atom with the carbon. So let me just highlight that. If you look at this carbon, it had an oxygen atom attached to it, which is replaced by a hydrogen atom in the product. So if you look at this hydrogen has replaced the oxygen. So this will be called a reduction reaction. The second method for reducing an alcohol is given here. You know that OH is not a good leaving group. It is very clear that the hydroxyl group is never a leaving group, but we can convert it into a good leaving group by its reaction to the tosyl chloride, and we can make it into a tosylate ester, and then tosyl group is a good leaving group in this case, which can be replaced and we get a reduced alcohol. So if you look at the reaction, you have an alcohol cyclohexanol, which on reaction with tosyl chloride in the presence of pyridine gives us a cyclohexyl tosylate. So tosylate gets attached here. This hydrogen of the alcohol and the chlorine of the tosyl chloride, they combine and an HCl molecule is removed from here. So if I write down like this, so this HNCl gets removed and the cyclohexanol gets attached to the tosyl chloride. So we can see in the cyclohexyl tosylate that the oxygen atom is from the alcohol. So if you use a powerful reducing agent like lithium aluminum hydride here, that will be converted to an alkane through an SN2 reaction. We'll look at the mechanism of this reaction in the next slides. So at the end, you have got cyclohexane from cyclohexanol. So you can see that the original reactant here, this carbon was attached to an oxygen, which is now having a hydrogen on it. So the oxygen is replaced by the hydrogen, and this reaction works mostly with the primary and secondary alcohols. If we look at the mechanism of tosylation, that is very important that we know how this reaction happens. A tosylate ester, we symbolize the tosylate ester as ROTS. So RO is from the alcohol and TS is from tosyl chloride. That is a product of condensation of this alcohol ROH with para-toluene sulfonic acid, that is symbolized as TSOH. So you look at this reaction, we have this alcohol which on reaction with para-toluene sulfonic acid combines to form this alkyl tosylate. So here this OH of the toluene sulfonic acid and the hydrogen of the alcohol combine to eliminate the water molecule from here and result in the formation of this alkyl tosylate. So now this tosylate is an excellent leaving group and it can be removed here by the attack of a powerful nucleophile. So we can use hydride as a nucleophile here and can easily substitute this whole tosylate group. Let's see. So if you look at this general reaction, this is an alcohol, and if we react it in the presence of pyridine, then you get this alkyl tosylate, and if you then use a hydride to attack on this carbon, the tosylate group will leave from here and your hydride will be attached here. So at the end you will get an alkane where the oxygen atom is replaced by the hydrogen atom. So how tosylates are made? They are made from alcohols. We do not really use the para-toluene sulfonic acid directly because it's uh, its salt, the tosyl chloride, which is more reactive and easy to use. So we use the tosyl chloride in pyridine, and it gives much higher yields than the para-toluene sulfonic acid itself. So if you use the tosyl chloride, its mechanism of action is similar. When the alcohol gets attached to it, the the mechanism is not that simple, like simply this H and this Cl is removed. So actually the pyridine attacks on this hydrogen and picks it up from here, from this molecule, and it gets positively charged, which in turn takes up the chloride ion with it, which is negatively charged. So this kind of complex is formed, and we have this tosylate ester where we can add a good nucleophile like a hydride, and we can um, remove this tosylate group, and the hydride would be attached to this R group. So if you look at the mechanism, we see that the CO bond of the alcohol remains intact throughout this reaction, and this oxygen of um, the alcohol is with the alcohol carbon chain. It is not being removed during this reaction. So what is the beauty of this reaction then? That the alcohol retains its stereochemical configuration, and in this reaction, which we saw on the previous slide, pyridine serves as an organic base to remove the HCl formed in the reaction. If pyridine would not be taking up this HCl, that would have been causing the side reactions by protonating the alcohol. So using the pyridine has this advantage that it removes the HCl formed and stops the side reactions. So if you look at the following reaction, you see that the tosylate group is being removed by the displacement of this tosylate with an iodide in an SN2 fashion, where you end up with the inversion of configuration. So if you look at the stereochemical features, when you react this S2 butyl tosylate, you end up with R2-butyl iodide, because this is an SN2 displacement which results in the inversion of configuration. As you might have studied the mechanism of the SN2 reactions in the previous course, stereochemistry and organic reaction mechanisms. So when the tosylate ion leaves, it is quite stable. That is why it is a good leaving group, because it has the resonance stabilized anion. So this tosylate ion is resonance stabilized and it leaves EZD from these reactions. So it is not necessary that you always use the hydride or the iodides. The tosylate leaving group can be displaced by a wide variety of nucleophiles, and you can get different products from these kind of reactions. So on the next slide, so you will see different reactions, that how general are the displacements of the tosylate groups. So in each case, the one thing is important, that R must be a primary or unhindered secondary alkyl group if you want to predominate the substitution over elimination reaction. So if you look at this slide, you have this ROTS, the alkyl tosylate, which can be displaced by using a number of different nucleophiles to give different products. So if you look at the first reaction, if you use a hydroxide as a nucleophile, you will end up with an alcohol. If you use a cyanide ion, you will get a nitrile at the end. So this is a very good reaction where you can get the products of the desired stereochemistry, because you know here is the inversion of configuration. So by using the appropriate R group, you can end up with the desired product. And if you use a halide, you will end up from an alcohol to an alkyl halide. If you use an alk oxide ion as a nucleophile, you will end up with an ether. Similarly, by using ammonia, you will end up with an amine salt. And if you use a hydride agent like lithium aluminum hydride, you will end up with an alkane, thus replacing the alcohol oxygen by a hydrogen. So this is a very important slide. You have to keep all these points in mind, that how by using different nucleophiles you can get different products. At the end of this lecture, I'll give you an exercise to practice different reactions. So this slide will be important, and you will need to use these different nucleophiles. So just keep that in mind to focus on these different nucleophiles and these reactions. So this was all about the reduction part. Now we move on to the oxidation. Similar to the reduction in organic chemistry, there are some commonly used oxidizing agents, some of which are given here. So potassium permanganate, KMnO4, is a quite common oxidizing agent in organic chemistry. Similarly, you can use chromic acid as an oxidizing agent. We have also seen ozone in different reactions, like you have seen ozonolysis reaction in the alkenes for the oxidation of the organic compounds. So these different oxidizing agents are used at different places as appropriate and where needed according to the conditions. If we look at the oxidation by KMnO4, potassium permanganate, that is the most common and probably the most applicable oxidizing agent which is discussed in organic chemistry teaching. So KMnO4 is a very strong oxidizing agent, and it is capable of oxidizing a wide range of organic molecules. Usually, it oxidizes the organic compounds to the appropriate carboxylic acids. I mean, if you start from an alkane, you will end up with a carboxylic acid. So, but the final product can vary on the conditions used. It is not necessary, or it's not compulsory that you always end up with a carboxylic acid, but generally that happens. So potassium permanganate oxidizes alkane carbon atoms, which contain sufficiently weak CH bonds. So for here we will have a look that the oxidation of alkanes is not possible in normal conditions. Like if you take up methane or ethane and you want to oxidize it with KMnO4, that won't be a good idea, because we need a CH bond which is weak due to something attached to it. In CH4 or the ethane CH3, there is no such hydrogen which is whose bond with the carbon is weak and which can be taken up by the permanganate. So to use these oxidation, we need to use those compounds in which the CH bond is weakened. For example, you can see the benzylic position. If the carbon is attached to a benzene ring, its bond with its hydrogen that becomes that becomes weak, and then we can use KMnO4 to oxidize this bond to replace that hydrogen by the oxygen atom. So these oxidizable alkyl benzene substituent, they can be simple dash CH3 like toluene, or any primary alkyl group such as ethyl group. If you put an ethyl group on the benzene ring, that will be a primary alkyl group, or you can use a secondary alkyl group such as isopropyl group on the benzene ring. So in all these cases, they will be oxidized to the relative carboxylic acid group, which we will see on the next slides. So here, if you look at the oxidation of this alkyl benzene, we have this benzene with an alkyl group attached to it. If we use KMnO4, we will end up with this carboxylic group directly attached to the benzene ring. So this benzene ring where the carboxylic acid is attached to it as the benzoic acid. The special thing in these reactions is whatever R groups you use here, you will end up with the same product, that is the benzoic acid. So R1 can be equal to R2, they both can be hydrogens. So that will be making it a toluene, and they can be primary, like R1 can be alkyl group and R2 can be a hydrogen, or they both can be alkyl groups, which will make it a secondary alkyl benzene. So in all these cases, you will end up with the carboxylic acid if you have used the primary alkyl group, primary alkyl benzene. If you look at the secondary one, the example given at the bottom here, you can see that these bonds shown in blue, that will be cleaved from here, and you will end up with this sort of molecule where there are 4 carboxylic groups on the benzene ring. If you oxidize this alkyl benzene shown here at the bottom, this is a secondary alkyl benzene, and you can see that the cleavage will be at these points where the blue bonds are shown. So it is important to note here that when the benzylic carbon is a tertiary carbon, for example corresponding alkyl groups such as these isobutyl group in the tertiary butyl benzene, the oxidation reaction does not happen. If you look at the example here, if you use this tertiary alkyl group where there is no hydrogen, that cannot be replaced by an oxygen atom. So this reaction simply does not happen. There must be a hydrogen atom which can be replaced by the corresponding oxygen atom to this benzylic carbon. If there is no hydrogen atom with this benzylic carbon, this oxidation with the potassium permanganate cannot simply happen. So if we look at the mechanism of this reaction, its mechanism was not known for quite a long time, and it was understood that this happens through some free radical mechanism, but this mechanism has been studied by someone whose reference I have given at the end. There was a PhD thesis in which this reaction was studied. And if you look at this toluene, if you treat it with alkaline KMnO4 and then with the dilute sulfuric acid, you will end up with the benzoic acid. So in this reaction, the most vigorous oxidant, according to that research, is the permanganate ion, MnO3 plus, positive charge. So with some contributing oxidation by the other ions like permanganic acid, HMnO4, and the permanganate ion, that is MnO4 negative. Such as so these reactions can happen with alcohols, aldehydes, or enols. So if you look at this mechanism, how it happens, the MnO4 negative ion, which is generated in the solution, that takes up protons and is converted to MnO3 plus, the permanganyl ion, and a water molecule leaves. This is a fast step. Then the slow step is where this permanganyl ion reacts with the your alkyl benzene. So this PHCr2H, that will be this toluene where two hydrogens are indicated as R groups. They can be any other R groups. As you know that the secondary alkyl benzenes also give this reaction. So this step will leave a radical where the alkyl benzene has lost a hydrogen, and now this place is vacant for an oxygen to take up. So this has generated a species which is the permanganic acid HMnO3 positive. Then this phenyl radical, the alkyl benzene radical, reacts with this acid and it takes up an oxygen atom from here, and that is how it is producing an alcohol which is further oxidized to produce a carboxylic acid, which is the benzoic acid in this example. So if you want more details of this reaction mechanism, you can go to the reference shown in the last slide and you can see the whole detailed mechanism. It was quite long and beyond the scope of this reaction. That would be definitely in an advanced organic chemistry course. So if you like further details of this reaction, you can go to the reference and see that how this whole reaction happens. So if you look, the thing we previously discussed, that any alkyl group that will be oxidized back to a carboxylic group on the ring under these conditions. It is not like that you use toluene and you are getting a benzoic acid, and if you used benzene with this propyl group and you will get a different propanoic acid. No, you will get the same carboxylic acid as you would get in the case of toluene. So if you look at this example where propylbenzene is treated with the potassium permanganate and dilute H2SO4, you are still ending up with the benzoic acid. That is because the alpha hydrogen is taken up by the permanganate, and this molecule cleaves from this position, from the benzylic, the position next to the benzylic carbon. That is why you always end up with the benzoic acid regardless of the alkyl chain you are using on the original benzene ring in the reactant. So here are some examples where you can see this happening, that this toluene, if you treat it with CHEM4, you will end up with the benzoic acid. If you treat the propylbenzene, you will still end up with the benzoic acid on oxidation by the potassium permanganate. And if you have this 6-membered cyclohexyl ring fused with the benzene ring, then you will end up with the benzene dioic acid, because now the cleavage will be at these 2 points. There are 2 alpha carbons and whose hydrogens can be replaced by the oxygen. So the cleavage will happen at these 2 points. But if you use the tertiary alkyl benzene where there is no alpha hydrogen that can be replaced, then there is no reaction. So that was the end of this lecture, and you have studied the oxidation and reduction reactions, oxidation reactions, where a hydrogen is replaced by the oxygen atom, and reduction reactions where an oxygen atom is replaced by the hydrogen atom. So after this, I have a few questions for your practice. So if you see, there are 2 questions. The first one is, you have to predict the products of these given reactions. Number A is cyclohexyl methanol. When you treat it with the tosyl chloride in the presence of pyridine, what will you get? Then you have to take up the product of this option A and treat it with lithium aluminum hydride, and tell what is the product of this reaction then. And then 1-methyl cyclohexanol on treating with sulfuric acid will give some product. You have to identify it, and then you have to take that product and hydrogenate it with the platinum catalyst and make another product after that. In the second reaction, you have to show how would you convert 1-propanol, and you also need to consider what reagents are needed to the following different compounds using the tosylate intermediate. So this is the practice about the tosylate intermediates, which I showed you earlier, that this slide is important and you will need this for the exercise questions. So you have to prepare these 4 different products. I hope you can make the structures of these products by reading their names, like 1-bromopropane, N-propylamine, and ethyl propyl ether, and butyronitride. So I wish you best of luck with this. I'll share the answers later on for this exercise, but you must practice this because that will be beneficial for you. And thank you very much for your attention. Here are the references which were consulted during the preparation of this presentation. So I consulted the Wade's Organic Chemistry. The chapter 11 in that book is about these reactions. And then this was the thesis I was mentioning during the lecture, the mechanism of permanganate oxidation of alkanes, arenes, and related compounds. So this was a thesis done in the University of British Columbia. If you want to have a look at it, you can go to this link, and there are 2 other links which have some important material related to this lecture. So I'll see you in some next lecture. Until that, Allah Hafiz.